Hello everyone, this is Brock Skaggs, and I'm going to make this video where we'll look at the same crank rocker mechanism and the same problem we did in the previous video where we were looking at the accelerations at different points on this mechanism. Specifically, we were wanting to know the total linear acceleration of point C, which is the connection point or the joint between the coupler here, link BC, and the rocker, link CD there, at a specific point in time. And so in a rather long previous video, we basically worked the entire problem out analytically, and so I guess I'll just show you this work here. And so we're assuming we've already done a velocity analysis here, and then we went through, looked at a relative acceleration equation. The acceleration of c is equal to the acceleration of b plus c relative to b. Broke each of those terms down into normal tangential components, looked at each of them of these individual terms, and was able to write those in terms of I and j notation. And when we didn't know the magnitude of the vector, we just represented it as a variable. Finally, solved the system of equations down here by breaking the one vector equation into two scalar equations. And then after determining the tangential component of c, we were able to determine the magnitude of the acceleration of c, the magnitude of that vector. And so we're basically going to work through the same problem in this video, except for instead of having to work through it all purely analytically, we're going to use some graphical techniques. And so what I've done is just create a new one-note sheet, as you can see here. The first part's exactly the same. Basically, the crank's going through a linear ramp from rest to a speed of 60 RPMs in 5 seconds there. We're zeroing in on a specific point in time, 4.47 seconds after this thing starts ramping up. At that instant in time, the angular velocity of the crank is 322 degrees per second, and the angular acceleration is 72 degrees per second squared there. And so we've already worked through the velocity analysis, and I've already retained some of the information from the acceleration analysis because it's basically going to be shared between the graphical as well as the analytical problems. And so first things you got to do is identify a few points. One point you're going to know some information about, the other point's going to be linked into what you're trying to solve for. And so just like in the analytical solution, the points of interest are C and B, where I can write my relative acceleration equation, as you can see here. Acceleration of C is equal to acceleration of B plus C relative to B. Also, sharing between the graphical and analytical approach, you'll want to break them into normal and tangential components in this case. And so here is the line doing that. And then again, you're going to have to look at each one of these vectors and see what you know about it. The nice thing, though, about graphically doing it is that you don't have to break them into I and J notation. Really, you just need to know the magnitudes and the direction, because then I can get into some sort of CAD utility. I'm going to be using AutoCAD today. And so then I can use things like snap to perpendicular, snap to parallel, or if I'm in SolidWorks, use the geometric relations in order to make things parallel, perpendicular, and so forth. So then you're just basically playing vector addition with drawing lines to represent the vectors instead of breaking it down to I and J notation and then solving a system of equations in order to solve for the unknown magnitudes. And so that's all we've got here. Same idea as far as figuring out the directions of the vectors, the normal and tangential components. Remember, the normal component always points back toward the center of rotation. Tangential component is always perpendicular to the normal component, and the tangential component always has to agree with the angular acceleration of the given length there. Exact same way that the tangential velocity of a given point always had to agree with the angular velocity of the length that it was sitting on. And so that's all I've done here. Using the same base equation, the normal component of the acceleration can be written as omega squared r, or v squared over r, and then the tangential component of the acceleration of a given point is r alpha for the base equations, just for the scalar magnitudes that I have in mind. And so this work should be basically a carbon copy at this point of what I've done in the analytical side. The only thing I did was I removed all the work for IJ notation, and then also I'm going to go ahead and make some notes down here on these two lines here that this is an unknown magnitude that we'll be looking for, as well as the tangential at C here. And so these will be things we try to solve for graphically. in order to work the rest of our problem. And so with that being said, let's go ahead and move over to the graphical side of things. And so here I'm using the same AutoCAD file that I originally drew the diagram for the mechanism and the current state it's in. I've also done some velocity analysis here. This line segments here just represent the straight line distances between the different points on my mechanism. And then I've got the velocity vectors here from that analysis. And so we'll just use the same file in order to do the graphical approach with the accelerations. And so again, the total purpose of this problem, as far as what we're trying to do, is determine the total linear acceleration of point C here. What is the magnitude of that vector, which in a sense is going to be the sum of the normal component and the tangential component. That'll give me A sub C, the vector, and then I need to figure out the magnitude of that vector. And so again, what we're going to do is work through this relative acceleration equation. And so what I like to do is start with the vectors that I know a lot of. And so here I'm going to jump to the right-hand side of the equation, and I'm just going to write this out in terms of vector addition, where I'm thinking tip to tail graphical vector addition. And so the first thing I have is the normal component of B. Well, through my hand calculations here, omega squared r, I was able to figure out the magnitude of that vector was 94.75 inches per second squared. Notice the direction is pointing from B to A. And so here inside of AutoCAD, I'll go to my vector known layer. I'll go L enter for that. It's going to point from B to A, so it's going to be parallel to this line segment. So I'll just pop a point in space here. Goes here, make sure my cursor picks up the parallel. There it is. And this was 94.75 for the magnitude. And so as you can see, just by drawing this one vector, it's going to be possibly quite a bit bigger than my velocity analysis. So I'm just going to slide this down here. Another thing I like to do if I have time is draw arrows on this. And so here, just put 3 for the length, 60. I'll mirror it across, just so I know which way this thing's pointed. Because of course in vector addition, it's important to know which is the front of the vector and which is the end of the vector, so to speak. And so there's that. This is the normal component of B. And so here I'll grab a multi-line text object acceleration, normal component of B. And we'll give ourselves a little label here. Just like so. And so there's the first vector in our equation, the normal component of B. So I've now drawn this vector here, the tangential component of B. Notice the magnitude is 3.77. As far as direction goes, you can see on my diagram, it's perpendicular to the normal component, and it's also going upward and to the left because, again, the tangential component has to agree with the angular acceleration of the length that it's sitting on. So I can think of point B being on the crank here. The crank has a angular acceleration oriented in the counterclockwise direction, and so the tangential B has to be pointing up and to the left, or in the second quadrant there. Well, again, the magnitude, it's not very big at all, 3.77 inches per second squared. And so really, what I'm going to have here is a vector. It's going to be pretty small. It's perpendicular, so I just snap to perpendicular there for the little stub line. Then I'll go parallel here. And this is only going to be 3.77, so it's not going to be much bigger than the legs here. These were 3. And so we'll make a much smaller triangle here. Let's go 1 at 30, mirror this across, and so this little vector here is the tangential component of B as far as the acceleration. So just moving around here inside of AutoCAD in order to get my label there. And so here you can see I'm doing tip-to-tail vector addition, and so now I've got the first 2 terms on the right-hand side of my vector equation here for that relative acceleration equation. So next, the normal component of C relative to B. As far as magnitude, we arrived at down here, 59.62 inches per second squared. As far as direction, well, we think of C at this instant in time rotating about point B, so it's going to be parallel to a line running between C and B. And again, magnitude 59.62. And so the direction part, I'll come back here to my line drawing. Still a known vector, so I'll stay on that layer. Here I'll snap to parallel right here. There, it picks it up. We said that was 59.62, I believe. Yes. And so it starts down here, and then the end point where our arrow will be up here and to the left. And so I'll move this guy down to where it starts at the terminal point of the tangential of B. Let's go ahead and put our arrowhead on it so we can remember where we were at. That looks pretty good. Here's that. And this completes our arrow. This is the normal of C relative to B. And so there is the label for us. And so we've done the first three now, normal at B, the tangential of B, and the normal of C relative to B. Now we have the tangential of C relative to B term. And so one thing I do know about that is that it's going to be perpendicular to this guy here, the normal of C relative to B. But at this point, I'm not sure whether the tangential component of C relative to B points up and to the right or down and to the left here. In the analytical version of the solution method, you basically just pick one of those two directions, and if you choose wrong, it'll come out as a negative sign in front of your magnitude. And graphically, you don't really have that negative sign popping out, so what's going to end up happening is we're going to look for the convergence or the crossing of two different line segments. And so one way you can do this, let's see if we can get something going here, is I could draw a line here that is perpendicular to this line here, the normal component. So then I could also use this for a, say, construction line. And so here I could draw a construction line just like so. And I'll delete this off. And so what I've done is in AutoCAD I've created a construction line, so it goes off in infinite length there, but it's on the right direction here. And so I'll be looking to see where the other half of my vector equation crosses this green line there. And so then I can, after the cross point, start trimming and determine the magnitude of the tangential of C relative to B. And so now that I've got the right-hand side of the equation, we start back working on the left-hand side. The normal at C, remember the normal at C, as far as the direction, it's going to point back from C to D. And so the magnitude of that is 141.9 inches per second squared. And so get back to my known vector layer, points from C to D. And so that was what this little sketch here was for. And so I'll snap to parallel on it. 141.9. There's my vector. And we have to now start this at the beginning here, and so it needs to start right here. That was the start point of the normal at B, that first vector. And we don't need two of these, so we'll move one of these over here. And this was the normal at C, right? 141.9, yes, the normal at C. So just update the label there, and let's go ahead and put our arrow in. Make this one a little bigger. The arrow's a little wider, but it should serve its purpose. Alright, so now that's the normal at C. I can hardly see the vector here, so let's bump this thing up. There we go. And so we've got the normal at C. Now we're to our last vector, the tangential at C. So the tangential at C has to be perpendicular to the normal. but we don't know if it goes off and to the left or up and to the right. It looks like we assumed up and to the left in our original drawing here. Here we can do the same thing we did with this tangential C relative to V1. That was the construction line before. Is I know it's got to be perpendicular, so I can use my snap to perpendicular inside of AutoCAD. I'll draw my little line segment here, and so that gets me the correct line there. And now one thing I could do is look at where is this thing going to intersect this other green line. Well, obviously if I go off and to the left, I can show you that quickly with a construction line. Off and to the left, basically these lines keep getting farther and farther apart, but down and to the right is where I'm going to have this intersection here. So that's what's going to give me the correct solution. Basically we're forming this vector polygon instead of solving the system of equations. And so now that I clearly see that, one thing I'll do is I'll just go and I'll extend this line segment here, and then I'll trim these off here. And so one thing I know is right here, let's say that is 6 for the arrowhead, maybe something like this. This was the direction of the tangential at C. So it goes down and to the right, 4th quadrant. There's that. There's the tangential at C. Label for us. Change the vector unknown layer here. And then the other one, this longer one down here, was C relative to B. Just like so. And just to continue our process here, it pointed this way. Alright, and so there are those two values here. We can trim this off really. There we go. And so now we've basically solved the vector equation really. This was the same action at this point as going into Sage that I did before and solving the system of equations. Now just to get the results, we'll go dim the layer, and 110.83 inches per second squared would be the interpretation there. And here would be 266.93 inches per second squared there. And so these values might be a little bit different from what I had in the analytical version. The analytical version, I've still got it here. I had 111.87. The negative sign indicates direction, which I can see by inspection in AutoCAD. The 111.87, and I've got 110.8 there. So roughly a unit or one off there. And then 266.93, 267.43, so roughly half off there, which isn't too bad agreement. Basically, I've got some rounding happening in terms of angles, I've got rounding happening in terms of magnitudes and so forth, and so I'm not too worried about that being slightly off there. So here, as far as getting to the question that we were originally asked was, what is the magnitude of the total linear acceleration of point C? Well, I could actually do that from this right here. Here I've got this and this vector, this red vector and this green vector here are the normal and tangential components, and they're oriented for vector addition, which is great. And so I'll just copy those off here. Just go ortho so they're directly in line. And so now I'm really looking at the hypotenuse formed by this right triangle here. And so just like so, that would be the magnitude. Then throw a dimension down here. There it is for us. 180 inches per second squared there roughly, which I believe is the value that I got in the analytical one as well. Here's our analytical results. Yes, roughly 180 inches per second squared. And again, roughly 180 inches per second squared here. Again, this being the acceleration to see the magnitude, and I won't draw the arrow in, but it's pointing up and to the right there. And so that's a quick run through of the graphical approach to solving that vector equation. As you can see, really it's doing the same thing as the analytical approach, except it's somewhat more convenient depending on what you're after. Instead of having to break everything down into I and J notation, generally you're already going to have the position analysis already done on your mechanism, so instead of having to figure out angles through trig and then break it into I and J notation in each individual vector, you get to take advantage of some of the power of the CAD software that you're using in order to just snap to perpendicular, snap to parallel, move vectors around in order to get the tip to tail addition there. Which, as you can see, can go relatively quickly, depending on the CAD proficiency, of course. And so thank you for watching this video. Hopefully this makes things a little bit clearer in terms of how the graphical approach is used in your acceleration problems. And so hopefully this helps you out in your studies.